Now let's continue to understand the write operation sizing as well. We'll do it real quick because we have understood the read operation. In the write operation, let's assume that there is 1 present at node 1 initially. 1 is nothing but VDD. If 1 is present here, that means a 0 would be present at node 2, correct? And what I'm interested in is writing a 0 at node 1. So 1 is present here at node 1. I'm interested to write a 0 at node 1, which is as good as writing a 1 at node 2. So as we saw the steps for the write operation previously, make your bit equal to 0 and your bit bar equal to 1 through your write circuit. We have already seen this in the previous clips. That means your V bit equal to 0 and your V bit bar equal to VDD. Then make your word line high or equal to VDD, which means your M3 and N4 transistor will turn on. Currently there is 1 at node 1. At node 1 there is a 1 which is VDD, which will go to this gate and turn on M2. So M2 is on. There is 0 at node 2, so this 0 goes here and M5 is on. So currently M5 is on, M2 is on, M3 is on and M4 is on, and I am going to zoom into M3 and M5 for my sizing, and it's a symmetric circuit, so exactly the same will be for the other half also. So let's quickly do this. I have zoomed into M3 and N5. M3 has one terminal which is nothing but bit, which is V bit, which is 0. Its input is nothing but word line, which is nothing but equal to VDD. M5 has node 2 as its input, which is nothing but 0, and the other terminal is connected to VDD, and this is node 1 where there is 1 present but we want to write a 0. Before we go ahead and understand this, let's quickly understand both these transistors are on. This terminal is at 0, this terminal is at 1, so this current will flow and this node will get discharged towards logic 0 due to charge sharing. At the same time, this transistor is also on. This is towards VDD, so this is trying to pull node 1 towards VDD, so there is a fight. And you want to write a 0, so you want your output to move towards this direction. That means M3 should be stronger than M5. Also, what does this mean is, if you want your M3 to be stronger than M5, or if you want to write a node value 0 at node 1, that means that if you want to write a 0 here, correct? That means M5 has to turn off and M1 has to turn on, because this will pull the output towards ground. If this is 0, that means this has to be 1, correct? Everyone agrees to that. For M1 to turn on, this has to be 1. This has to be 1 means M6 has to turn on and M2 has to go off. Don't get confused at all. It's very straightforward. Currently, you have M5 and M3 which are on. This is off. This guy is also on and this is off. Now, if you want to change this VDD to 0, that means this NMOS transistor has to turn on, correct? And that also means this M6 transistor has to turn on. Or in simple words, what we have to ensure that is this transistor M2 has to go off. So the node voltage at 1 should be adjusted in such a way that it goes below the threshold voltage of M2. It should be equal to or less than the threshold voltage of M2, and if that happens, this transistor will go off and this will turn on. So this is what I have written. The node voltage at 1 should be less than or equal to the node threshold voltage of M2, because I want to make this off. Technically it should be less than. I've just written for representation to be less than or equal to. If it goes below, then this transistor will go off. Now let's see the region of operation. M3, let's zoom into this. The transistor is on. We have to just find linear saturation, so VDS dash VGS minus VTN. We know that due to charge sharing, after some time this node and this node both will have the same potential. That means drain and source will have a difference voltage which is nearly equal to 0. So 0 dash gate voltage is VDD, source voltage at that point of time would be, as this is the source, right? So the source is at 0 minus VTN. So this is nothing but less than sign, which means that my M3 transistor is in linear region. I can also assume my node voltage V1 to be equal to VTN, because this is the point of analysis. Then this is VTN minus 0, which is again going to be less than or equal to this, correct? So it's in linear region. If you have not followed this, it's fine. Let's assume that drain and source voltage will have the same potential after some time. M5 region of operation. Again, the transistor is on. VDS dash VGS minus VTP. If you see drain voltage here, it's node 1, which is going to go towards 0, or we want to write a 0. So drain voltage is 0 minus the source voltage, which is VDD dash VGS. Gate is at 0. So that's nothing but 0. Minus source, which is nothing but at VDD. So 0 minus VDD minus VTP. Let's put the values. VDD is minus 1.8. 1.8 minus VDD is minus 1.8. Minus 1.8 minus of minus 0.6, because VDP is a negative value. That will make it minus 1.2. Does everyone get that? So this is minus 1.8 minus of minus 0.6, that is 0.6 positive, minus 1.2. This will be again a less than sign, correct? That means PMOS operates in saturation region and MOS operates in linear. Let's go ahead and just equate it like we did for read operation. I've written the equation for saturation, I've written the equation for linear. For M5 I've put what is VG, what is source. For M3 I've put what is gate voltage, what is source voltage, and what is drain voltage, and now I'm just going to substitute this in the above equation. Let's quickly do that. And we just saw that V1 should be less than or equal to VTN, so I'm putting V1 equal to VTN and just solving this. So Kp of 5 by 2, gate voltage is 0, minus VDD minus VTP the whole square equal to Kp3 by 2 twice VGS, which is nothing but VDD, minus VTN. VDS is nothing but V1, which is nothing but VTN. So into VTN minus VTN the whole square. And now if we rearrange, we know that we want this, right? I can easily write this W by L of M3 upon W by L of M5 should be greater than 1, correct? So we can put this in terms of Kn, because W by L of M3 is nothing but mu n COX W by L. Okay, we'll do it in terms of Kp here and then I'll tell you what we are doing. So this is what it is. Now I'll just rearrange the terms. So Kp of 5 upon Kp of 3 equal to, or rather less than, because M5 should be less than M3 W by L. So this is less than sign, twice VDD minus 1.5 times VTN into VTN, simple mathematics, upon VDD plus VTP the whole square. And now if I bring it in terms of W by L, now you know that the mobility will change, correct? So we'll just add that one term also. So W by L of M5 upon W by L of M3, the same term with the mobility thing included, less than mu n by mu p, and then exactly the same term, twice VDD minus 1.5 times VTN into VTN upon VDD plus VTP the whole square. What I have done is nothing but just put here mu n by mu p when I consider W by L of 5 upon W by L of 3. That's exactly what I've done here. So I hope you have followed the sizing in SRAM for the read and the write operation. Stay tuned for further clips and thank you very much.